Okay, so we're going to be taking a quick look at some concepts that go along with patterns in the atmosphere. I think this will hopefully help you understand why some of the patterns exist and also hopefully know which patterns are important. This is one of the things you were supposed to learn this year. So here we go. Quick intro. We're going to start off by talking about temperatures in the atmosphere. Before we do any of that, I need you to visualize a human being standing at a camp out, okay, with three campfires. And when they're standing near one of them, obviously they're going to be nice and toasty. As they move further away, they would get cooler and cooler until they started getting close to the second one. Follow my mouse cursor. It's our happy little person here. When it gets to the second one, it's going to be warm. As it starts moving away from it, it is going to be cold. And then as we get closer to the third, it would warm up again. The reason I'm talking about campfires is because we have essentially three of our own nice little campfires. We'll call them hotspots in the atmosphere. We have the surface of the Earth down here. It is hotspot number 3 on our list here. We have the ozone layer, which is actually in the upper stratosphere here. It's kind of a layer of gas made up of 3 atoms of oxygen. It's called O3, just like the air we breathe is O2. And ozone is kind of a cool gas because as sunlight passes through it, the molecules get very excited. And we should know at this point in the year that excited molecules with lots of molecular movement, we would say have a higher temperature. In fact, temperature is just the average amount of kinetic energy of a substance. And that is our hotspot number 2, the ozone layer. And that's because as the sun passes through it, it warms those gases. Hotspot number 1 on our list, so the very top of our planet. And that is where the sun is first interacting with the gases in our planet. And because of that early interaction, the gases move at an incredible speed. Some of the fastest average speeds of any place in our atmosphere. You can see here this red line, which tracks temperature, is at the far right on the list, around 80 degrees Celsius. So we're going to trace this up from the surface of the planet. So if we start down here where we live, it's pretty warm in general compared to the rest of the atmosphere. But as we move up through the troposphere, you're going to notice the whole time we're going through the troposphere, it gets colder. In fact, that is why this layer of the atmosphere, the troposphere, is characterized as it is. The only thing this really has in common is that it gets colder the whole way up. As soon as it starts warming, as we move through the stratosphere, we approach our hotspot number 2, and boom, eventually it stops getting warm. You'll notice this is the entire stratosphere. This whole area where it is warming is the stratosphere. As we move away from our ozone layer, it gets cooler and cooler till eventually we reach a point where it starts warming again. That is the cutoff for our mesosphere. And the mesosphere transitions into the thermosphere, where the temperatures start to increase again as we move towards our other hotspot, which is the edge of our planet. Some key things to note with this: these trends are responsible for why we call these layers of the atmosphere what we do, but there are also some other properties that are important to note within these layers of the atmosphere. The other thing I want to point out is just kind of a fun fact. Even though the temperatures up here are crazy, crazy hot, if you were up there, there are so few air molecules up at this height on the top of the thermosphere that you would probably not experience a great deal of that heat, meaning there's so few air molecules that they would not likely vibrate your own molecules and increase your temperature that much. So that's just an interesting fact. Next thing we're going to talk about are some patterns regarding air pressure. Now, thinking about air and pressure is a really weird concept, and it's hard to think about air in general because we can't see it. So instead of talking about air, I'm going to start off by talking about feathers. So let's look at our little stack here. This image is intended to represent what the air does as you move higher and higher, and it shows how down here at the bottom it's a little more squished together. But we're going to use a more creative way of thinking about this. I want you to pretend for a second that I snap my fingers and every air molecule turned into a feather. It might sound cute and fun, like some gigantic pillow fight, but I assure you that would not be the case. Even though feathers are light, if we were to stack 120 kilometers worth of feathers on top of us, we would understand quickly that, wow, feathers really do have mass. In fact, the mass would be so intense that it would squash us. It would be pretty tremendous. It would be a horrific way to go. Death by feathers. So that concept is very important. The idea that even though air is light, just like feathers, it has mass. And even though it's light, the fact that there are several miles of it piled on top of our heads means that it's going to add up to quite a bit of pressure. The air itself presses around us. I've had kids ask, well, how much does the air press around us? So let's pretend that we had a 1 inch by 1 inch cube that weighed 15 pounds. Okay, technically air presses down with about 14.7 pounds per square inch on everything it touches. That means that your body is used to having about close to 15 pounds on every square inch of you, and that's just from all the air that's piled in around you. If we look down here at the bottom of this diagram, we will see that this air is more compacted, and that is because it's got lots of other air piled on top of it. It's kind of getting squished down here. So standing down here, the air is pressing pretty hard all around us. Like I said, about 15 pounds per square inch, 14.7 pounds per square inch. As we go higher and higher, we have less air on top of us. Therefore, the air would be pressing a little less hard around us. Think of our feather analogies. By the time you got up to the top, you would hardly experience anything in terms of pressure from those feathers, aka air. And that's what we mean here. So the general pattern in the atmosphere, the lower you are, or the closer you are to the surface of Earth, the higher the air pressure, and that's because you have more stuff piled on you. The higher you go, the less pressure you would experience. I'm sure some of you have experienced this as you were climbing a mountain or going up a steep hill in your car, or maybe even flying in an airplane. You might experience your ears popping, and that is just your body trying to adjust to not quite having that same 14.7 pounds per square inch pressing down on your ears. There are some people who, if they go up in altitude way too quickly, they get tremendous headaches, and part of that is to do with the air pressure. Part of that is to do with the amount of oxygen they're receiving, but we'll talk about that here in a second. Moving on, so pattern with air pressure, higher you go, the less air you have pressing around you. The next concept is water vapor in the atmosphere. This is an easy one. Almost all of the water vapor is trapped down at our lowest level, which we call the troposphere. So the troposphere here is where we live. It's where we experience our whole life. Even if you're flying in some of the highest commercial jets, you're barely going to breach the top of the troposphere. So the troposphere contains almost all of the water vapor. It's easy to remember. Almost all of the water is trapped down by us. I had kids ask me why. Why would all the water be trapped down by us? Why doesn't it just keep drifting up? Well, the answer is it gets so cold as we approach the top of the troposphere that the water condenses into liquid and usually will fall back down around 6,000 feet, which is pretty low. So a lot of our lower level clouds, stratus clouds and cumulus clouds occur around 6,000 feet. As we go up higher and higher, even the very spread out water molecules get so cold that they latch onto dust particles, they freeze to it, and will eventually fall back towards the surface. By the time you've gotten it towards the middle portion of the stratosphere, there's so little water vapor that it's not even worth talking about. So as a general rule, almost all of the water vapor on our planet is trapped in the troposphere. Small trace amounts exist in the lower part of the stratosphere, but again, it's barely worth talking about. As you move up further and further, you have less and less water. So the lower parts of the troposphere have the most water, and the highest parts of our mesosphere and even thermosphere have almost no water whatsoever. Something to think about. Now we'll talk about the composition of the atmosphere. That word means essentially what is our atmosphere made of? A lot of people think that it's made of all oxygen. That is not true, thankfully. We would explode every time, or we would have major, major problems every time someone lit a match. And that is because oxygen is a volatile gas. It is capable of exploding under the right conditions, and adding fire to it is a very dangerous thing. So Nitrogen, however, is what we call an inert gas, and nitrogen accounts for about 78% of our atmosphere. So that's a good thing. Most of our atmosphere is a really stable gas, and that's important. 21% of our atmosphere, almost everywhere you go, is oxygen, 0.9% argon, and the rest accounts for that last 0.1%. It is not very much at all. This would be things like neon, xenon, krypton, and those gases exist in very small concentrations in our atmosphere. There is, it's important to point out, down by the surface, some water vapor mixed in, so that would change the composition of our air as well. But in general, these are the patterns that are true no matter where you are in our atmosphere. I've had students say, well, then why do people pass out when they go to like the tallest mountains? The reason is there is less of that air mixture up on the tallest part of the mountains. It's like saying this. If I told you that you could have 21%, and that's our oxygen, 21% of a jar full of jelly beans, you would get quite a few jelly beans. But if I said you could have 21% of a jar that only has one jelly bean, you're not getting much. The same is true as you climb a mountain. The higher you go, the less air is available for you to breathe. But oxygen still accounts for 21% of it. Nitrogen still accounts for 78% of it. And argon still accounts for 0.9% of that. So that is the composition of our atmosphere. I want to intro a brief thing here for you. If we take a look at this interactive atmosphere, I want to go through these key patterns one more time, and that's because you're going to be utilizing the same data set to investigate some of the properties of the atmosphere. So let's start off down here near the surface. I'm going to click the troposphere. That is the layer that's closest to us. Again, notice the reason it is characterized the way it is, all the temperatures are getting colder. So as I go higher in the troposphere, it gets colder. The pressure decreases as I go higher. And again, that's because there's less air piled on me here than there is down here. Notice what I said about the composition. The composition stays the same, excepting the water vapor, but the same amount of nitrogen, oxygen, and argon exists in all parts of this. As we move into the stratosphere, you're going to notice the temperatures start getting warmer, and that's because we're moving back to that second hotspot. So all the way from a nice frigid negative 55 degrees Celsius all the way up to negative 10. Still cold, but definitely warmer. So there's warming temperature in the stratosphere. Composition stays the same, minus or excepting that small amount of water vapor in the lower levels. And the pressure continues to decrease. As we go to the mesosphere, the temperatures are decreasing, as we move away from the ozone layer. The pressure is decreasing because that's what it does throughout the whole atmosphere as we move up. And the composition of the atmosphere stays the same. In the thermosphere, the temperatures are increasing. Fun fact, the thermosphere has both the coldest temperature and the hottest temperature. And that's an interesting reason to call it the thermosphere. It has the widest range of thermal energy. The composition stays the same and our pressure continues to decrease. If we make a quick comparison of the troposphere's pressures, boom, very, very high down at the surface, to the top of our atmosphere's pressures, you'll notice there's essentially very little air pressing in around you by the time you get up to this level. Those are some of the patterns that you're supposed to be aware of within the atmosphere. Hope you enjoy exploring it. You guys will be doing some cool stuff to look at that in a little bit more detail. If you have any questions, ask your teacher. Thanks.